In this video, we solve problem 13.5.506.xp from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're told that to let theta be the angle between equal sides of an isosceles triangle and let x be the length of these sides. Then we're told that x is increasing at 1/2 of a meter per hour and theta is increasing at pi/90 radians per hour. We're asked to find the rate of increase of the area dA dt when x equals 8 and when theta equals 3 pi/4. We're asked to round our answer to 2 decimal places. So we want dA dt. Since x is being measured in meters, our area is going to be measured in meters squared. So this is going to be some number of meters squared per unit time. And then if I'm trying to figure out what the units are for time, I can just look at the rates of change that they gave me. They told me that x was increasing at a rate of 1/2 of a meter per hour. So as soon as they said rate, I'm thinking derivative. And when I see those units, a meter per hour, that is a change in length per unit time. So that's dx dt. And we're told that that was 1/2. And then here we have theta is increasing at pi/90 radians per hour. So when they say it's increasing, that means it's positive. And we have that there. So if these units are, or if these rates of change are measuring t in hours, our area rate of change should measure that time in hours as well, or it generally will. So that's what we want. Now, since we are studying functions of several variables and the appropriate chain rules, we will find, in order to solve this problem, we will find the area in terms of x and theta. And then once we have the area in terms of x and theta, we can use the appropriate chain rule to find the derivative of the area with respect to time. So remember how this works. If you have an isosceles triangle, that means 2 of the sides are the same length. And because of what we know about triangles, we know if this side has length x and this side has length x, this angle and this angle would have to be the same measure as well. So the height of this triangle, if I'm looking at it this way, just goes straight down from that. And that height is going to intersect the base like halfway from either side. So this is the height of the triangle. That's the base of the triangle. And that relationship where half of the base is equal to this length, or the length of the base is here. The length of this piece is the length of half of the base. The length of this piece is the length of half of the base as well. That's going to hold because of the symmetry of the isosceles triangle, because this angle is equal to this angle. Now we're told to let theta be the angle between the equal sides of an isosceles triangle. So that's this larger angle. If I put this line segment here that's coming down at a right angle, then on either side of that line segment, the angle will be theta divided by 2. So with these angles each being theta divided by 2, and this being a right triangle where x is the hypotenuse of that right triangle, it's opposite the 90-degree angle, we can use that to find the base and the height in terms of x and theta divided by 2. And once we have the base and height in terms of x and theta, well, that's going to be enough to find the area in terms of x and theta. And then we can use Calc 3 methods in order to solve the problem. So let's go on. Let's figure this out from here. If I want the height, which I'm going to label h, well, I know that the height is the adjacent side, or the side adjacent to that angle theta over 2. Since I'm interested in the adjacent side and I know the hypotenuse is equal to x, I would use the cosine function. The cosine of theta over 2 is related to the adjacent side and x. that's equal to adjacent over hypotenuse. The adjacent side is the height, and the hypotenuse is x. So if I want to find the height of that triangle in terms of x and theta, I'll just multiply both sides of this equation by x, and I get x, or h equals x times cosine of theta over 2. Okay. Now for the base, remember if this is the base, this is half of the base right here. Well, half of the base is opposite that theta over 2 in our triangle. So I would use the sine function there. The sine of theta over 2 is opposite over hypotenuse. In this case, the opposite side has length 1/2 of b, where b is the length of the base. The hypotenuse is x. So if I want to solve for b, I can multiply both sides by 2. That will get rid of that 1/2, and then multiply both sides by x. That'll get rid of the x there. And so what we have is that the base is equal to 2x times sine of theta over 2. Now, since I have the base and the height in terms of x and theta, we can put those two pieces together to find the area. The area of that triangle, our isosceles triangle, is 1/2 base times height. So it's going to be 1/2 times the base, which is 2x, times sine of theta over 2, times the height, which is x, times cosine of theta over 2. And actually, 2 times sine of an angle times cosine of that angle is a sine of double the angle. So this is going to give me a 1/2. X times x is x squared. And my angle in this case is theta over 2. So when I double that, I'm going to have an angle of theta. So I'll have sine of theta here. And again, that's because 2 times sine of an angle times cosine of an angle is sine of double that angle. And in this case, my angle is theta divided by 2. Theta divided by 2 times 2 would just give me a theta. So here's my area as a function of x and theta. And that's how we start this problem. Okay, so now let's get back to the question that they were asking us. They said, find the rate of increase in the area when x equals 8 and theta equals 3 pi over 4. Well, since this is a function of two variables and x is a function of t and theta is a function of t, dA dt is a sum of two terms. It's the partial derivative of a with respect to x times dx dt plus the partial derivative of a with respect to theta times d theta dt. That's one way of doing it. If you prefer, you can think of that in terms of the gradient. You can say that that's the gradient of a evaluated at x of t and theta of t, dotted with the vector with components x prime of t and theta prime of t. You can do it that way or you can do it this way. I think this way is simpler in this context. Okay, so now we need to know what the partial derivative of a is with respect to x. Well, that's easy enough. We're taking the partial derivative with respect to x of 1/2 x squared times sine of theta. The 1/2 is a constant. Sine of theta is being treated as a constant in this context. So this is a constant times x squared. The derivative of a constant times x squared is that constant times the derivative of x squared, which is 2x. The 2 and the 1/2 reduce, and we just end up with x times sine of theta. And then the partial derivative of a with respect to theta is handled very similarly. This is a constant times sine of theta as far as we're concerned when we're taking the derivative with respect to theta, partial derivative with respect to theta. The derivative with respect to theta of a constant times sine of theta is that constant times the derivative of sine of theta, which is cosine of theta. So those are our partial derivatives. We can substitute those here and here. If you want to, you could also just substitute in the values of theta and the values of theta and x that were given to us. So that's a possibility as well. Actually, let's do that here. The partial of a with respect to x evaluated at x theta equals 8 and 3 pi over 4 is x, which is 8 times sine of theta, which is 3 pi over 4. So if I'm over here, and this is 3 pi over 4, that's a 45-degree reference angle. So this is going to be a 1, 1 square root of 2 triangle. The x is negative in quadrant 2, the y is positive. So the sine is opposite over hypotenuse, or 1 over square root of 2. So we have 8 times 1 over square root of 2. Of course, you can rationalize if you want to. So we have 8 root 2 over 2, or 4 root 2. Now that is a change in area, so that's meters per second, or excuse me, not area, meters per second, meters squared per change in x. So that's meters squared per meter, but you don't want to simplify it to meters. You want to think of this as how much area is changing. Area is changing by 4 times the square root of 2 meters squared for every 1 unit change in area, or excuse me, 1 unit change in x, when x is equal to this value and theta is equal to that value. Okay, instantaneously, that rate of change is going to change as soon as x changes. And then we want to find the partial of a with respect to theta now, evaluated at x equals 8 and theta equals 3 pi over 4. And we'll have 1/2 times x, which is 8 squared, times cosine of theta, which is 3 pi over 4. Of course, 8 squared is 64. And cosine is going to be -1 over square root of 2, or if you rationalize, negative square root of 2 over 2. And what we end up with is the 64 divided by 4, which we know is 16, times a negative square root of 2. So we have negative 16 square roots of 2 there. Okay, so we know this quantity, partial of a with respect to x at that point. We know this quantity at that point, at that particular value of theta and that particular value of x. So we can just substitute those into this formula, and then we'll be done. So I'm not actually using this time. The partial of a with respect to x at x equals 8, theta equals 3 pi over 4 is 4 times the square root of 2, and dx dt is 1/2. Then we're adding the change, or the partial derivative of a with respect to theta, which is this negative 16 square roots of 2 times pi over 90. It actually doesn't simplify very nicely at all. That's okay. So we'll have the partial derivative of a with respect to t is 2 times the square root of 2 minus 16 pi times the square root of 2 over 90. I mean, you could divide this by 2, you could divide that by 2, but it's not really getting us very far as simplification is concerned. I guess we could multiply this one by 45 over 45 to get a common denominator. And so what we end up with is 90 square roots of 2 minus 8 pi times square roots of 2, all divided by 45. And that's going to be meters per hour, meters squared per hour. But they wanted a decimal approximation. So let's get a decimal approximation. We have 90 minus 8 times pi times square root of 2. Whoops. divided by 45, and we had approximately 2.04 meters squared per hour. So I think the key is to draw this triangle in this way, and then just use trig. Cosine will allow us to find the height here, and the sine will allow us to find the length of half of the base, which we can double to find the base. And then when you put those pieces together, you get something that looks like this. You don't have to use the double angle formula for the sine function if you don't want to. You could just use this. That would be fine as well. You're going to get the same answer. Just when we use the double angle formula, it makes the area formula a little bit cleaner. Then we just needed to find these two partial derivatives. We needed to evaluate them at the x value and the theta value we were given, and then multiply them by the appropriate rates of change to get the rate of change of area with respect to time.